Hello everyone, welcome to the lecture number 4. In this lecture, we will start with another theorem which is very important for moment of inertia topic, and that theorem is called perpendicular axis theorem. Let's see what is the theorem. Suppose this is a disc of mass m and the radius is r. With respect to this axis or the z axis which is going outward from the board, with respect to that axis, moment of inertia is mr square by 2 that we have already found out in the last video. Now, this perpendicular axis theorem says Iz, the moment of inertia with respect to z axis, will be the sum of moment of inertia with respect to x axis and moment of inertia with respect to y axis. Now we have defined x and y axis like this. Basically we are interested in the rotational property of a disc if it is rotating like this, not with respect to the z axis, but it is rotating like this. So see, here with respect to the x axis and y axis, it is looking symmetrical. Symmetrical means with respect to x axis, whatever the moment of inertia will be, the y axis same moment of inertia will be for y axis as well, because it is symmetric. The disc doesn't know what is x axis and what is y axis. We are defining that. So with respect to y axis also and with respect to x axis also, the moment of inertia will be same because it is symmetrical. So we can write that in this case Ix equal to Iy. So let us put that mr square by 2, that is equal to Ix plus Ix or Iy plus Iy. So 2 of Ix will be mr square by 2. So Ix, which is equal to Iy, that is becoming mr square by 4. Right now it is very easy to find out with this theorem that what is the moment of inertia with respect to another axis, x axis and y axis, which is perpendicular to the initial axis. Now let us consider this to be a ring of mass m, and as the same radius is r. Now we know about this axis which is passing through the center of mass perpendicularly, that is mr square only. So what will be the Ix or y? Suppose it is a ring and we are interested about the ring property if the ring is rotating like this, not like this, rotating like this. Then from perpendicular axis theorem, Iz is mr square, that is the sum of Ix and Iy. Or as x and y axis are symmetrically dividing this ring, we can write that Ix equal to Iy. So here also same thing will be there, 2Ix equal to mr square. So Ix equal to Iy, that is equal to mr square by 2 for the case of a ring. Now we will try to find out what will be the moment of inertia of a hollow sphere. The hollow sphere of mass m and the radius is r. Now think that this is a hollow sphere which is rotating with respect to z axis, or we are interested in finding out the rotational property with respect to z axis. Now see, a hollow sphere means inside there is no mass, nothing is there. All the masses are located at distance r from the center. Center means this point. But as we are interested in the rotational property of the hollow sphere with respect to this axis, see, some masses are rotating like this and some masses which are rotating like this, some masses which are rotating like this. So from the axis of rotation, see that distance for this case it is less, for this case it is the maximum, that is r, for this case it is less than r, less than r. And observe one thing, that this distance is varying. If I take an angle theta from here to consider a ring, see with theta, if I increase the value of theta from 0 to pi means here, exactly here. So from here to here, the distance of the ring which is rotating with respect to the axis is increasing from here to here, then again it is decreasing from here to here. So for a general ring, if we consider, which is at distance theta and d theta, this will constitute one ring like this, because it is a hollow sphere. This ring will be considered. So for this ring, what will be the mass which is rotating with respect to the z axis? If it is theta, see, this is r. The distance of the ring from the center of rotation is this one only. This is r sin theta. So all the rings are creating different radius, which is varying with theta only. For theta equal to 0, the ring it is subtending, that is having 0 radius. If the theta is becoming pi by 2, then we are interested in this ring, and the radius is r only. So pi by 2 value of sin theta is 1 only, so we will be interested in r ring. If we eventually go to the pi, then the radius of the ring will be also be 0. So right now we are considering one general ring which is at distance, angular distance theta from this vertical z axis. Now what is the mass of this ring? See, if we unfold it like this perimeter is becoming 2 pi. Now the radius is r sin theta. So 2 pi r sin theta will be the length of the ring, and this width is this one. This is r into d theta, because as you know s equal to r theta. So for d theta angle, what is the small width? R d theta. So this is r d theta. So right now, what is the area of the ring? Area of the ring is 2 pi r sin theta into r d theta. That is becoming 2 pi r square sin theta d theta. That is the small area dA. Now as it is a hollow sphere, all the masses are areal masses. So what is the total area? 4 pi r square total area. So for 4 pi r square area, mass is m. So for this small area dA, the mass will be, so area is 2 pi r square sin theta d theta. So mass will be m by 4 pi r square into 2 pi r square sin theta d theta. So small mass is becoming, dm is becoming m by 2 sin theta d theta. So for a small ring having mass dm and the radius is r sin theta, what is the small moment of inertia? For a ring, the moment of inertia is dm into the radius square. Now right now the radius is r sin theta. So r sin theta square is the moment of inertia of the ring, just one small ring, di. Right now to find out the total moment of inertia, I have to do the summation of all the small rings, di. So we will just put the value of dm here, that is m by 2 sin theta d theta r square sin square theta. Now the variable is theta, is varying from 0 to pi. If theta is varying from 0 to pi, it will cover all the hollow sphere and we will be able to find out the moment of inertia. So m r square by 2 will come out of the integration because it is a constant for a particular sphere, and it will be integration of sin cube theta d theta. Theta is varying from 0 to pi. And now we will be able to do the integration. M r square by 2, if we multiply with 4 in the numerator and denominator, we will get 4 sin cube theta. That is basically 3 sin theta minus sin 3 theta, the formula d theta, from 0 to pi. We'll do the integration. Here it is becoming m r square by 8. 3 sin theta d theta integration is minus 3 of cos theta minus, it will be plus cos 3 theta by 3 from 0 to pi. We'll put the values. Pi if we put, we'll get 3. plus will get 3, and this cos 3 pi minus cos 0, that is of minus 1, so it is becoming 6 minus 2 by 3 multiplied by mr square by 8 outside, 18 minus 2, that is 16 by 3, 16 by 3 into mr square by 8, so that is becoming 2 by 3 of m into r square. So that is our value of the moment of inertia of a hollow sphere having mass m and the radius is r, 2 by 3 mr square. Now let us find out what will be the moment of inertia for a solid sphere of mass m and the radius is r. See, one solid sphere constituted of many small hollow spheres which are concentric but with varying radius. Right now, all the hollow spheres are the function of radius r. Now for a hollow sphere, you know the moment of inertia with respect to the axis which is passing through the center, that is 2 by 3 into m into r square. Now, without even finding out the moment of inertia of a solid sphere, you will be able to tell that the moment of inertia of a solid sphere of the same mass and the same outer radius, it will be less than that of the hollow sphere, because there will be some masses which will be distributed towards the axis of rotation also. So it will be definitely less than the hollow sphere. As I told, that moment of inertia depends on the mass distribution away from the axis. If some mass is distributed towards the axis, then the moment of inertia will be less. That is in the case of the hollow sphere and the solid sphere. Now see, we will consider one general hollow sphere which is at radius r. As I told that one solid sphere is constituted of many small hollow spheres of varying radius, and those are concentric. We will first find out what will be the mass of a general hollow sphere which is located at small r distance from the axis of rotation, r and dr. So there will be one hollow sphere which is having thickness of dr at distance small r from the axis of rotation. The thickness of the hollow sphere will be dr. Now, what will be the mass of the hollow sphere? If we know the mass of the hollow sphere, we can write that the moment of inertia of the hollow sphere is 2/3 of that mass into the radius square, and then eventually we can do the integration and we can find out for the entire solid sphere what will be the moment of inertia. As you know, the volume of a sphere is 4/3 of pi into r cube. So small volume, the differential volume, that will be 4/3 pi into 3 r square dr. So that is eventually becoming 4 pi r square into dr. That is a small volume. Now see, the small volume or differential volume is multiplication of 4 pi r square into dr. As I told, we are interested right now in a general hollow sphere which is having the thickness of dr. Basically we are multiplying that small thickness with the area of the hollow sphere, and the area of the hollow sphere is 4 pi r square. So that is creating a differential volume. So if it is a uniform solid sphere, then we can tell that mass is uniformly distributed throughout the volume. So for volume V, the mass is m. So volume V means 4/3 of pi capital R cube, the mass is m. Now for the differential volume, what is the mass? 4 pi r square dr. What is the mass? M by 4 pi r cube by 3 into 4 pi r square dr. That is 3m by r cube into r square dr. That is the small mass of the hollow sphere. Now we got to know that small mass of the hollow sphere is dm is 3m by capital R cube into small r square into dr. Now for that hollow sphere, what is the small moment of inertia? 2/3 of m, here m is dm, into r square. We can put the value of dm from here, that is 3m by r cube, r square dr, r square into r square multiplied, that will become r to the power 4 into dr. Now that is for differential hollow sphere, that is the small moment of inertia. Now if I want to find out what will be the total moment of inertia of the solid sphere, then I have to integrate from r equal to 0 to r equal to capital R. Then only we will be able to do the summation for all the moment of inertia of the hollow sphere, and we will be able to find out the moment of inertia of the solid sphere. If we do the integration di, then we have to integrate, it is becoming 2m by r cube, integration of r to the power 4 dr, varying from 0 to capital R. Let us do that. 2m by r cube, r to the power 4 dr, integration is r to the power 5 by 5, limit is 0 to r, capital R. Right now 2m by r cube, it is becoming r to the power 5 by 5 minus 0. So basically it is becoming 2m by r cube into r to the power 5 by 5. So it is becoming 2 by 5 m into r square. That is the moment of inertia of a solid sphere of mass m and radius r, which is rotating with respect to the axis, which is passing through the center. As I told initially, before starting the derivation, or before starting to find out what is the moment of inertia of the solid sphere, that it will be less than that of the hollow sphere. See, it is less than that of the hollow sphere, because here mass is distributed towards the axis as well. That is why the entire summation of all the moment of inertia, small moment of inertia, that will be less than this one. That is we are getting. Thank you.